Hello everyone, and welcome back to the How Machines Work series. So far, we've learned about forces, motion, Newton's laws, and torque. These concepts help us understand how machines move and how they create rotational motion. Today, we're going to answer another important engineering question. How much work does a machine actually perform? To answer that, we'll explore three fundamental concepts: work, energy, and power. These ideas allow engineers to measure machine performance and compare different systems in a meaningful way. Before we begin, let's review what we've covered so far. We've studied force, motion, Newton's laws, and torque. Each of these concepts helps explain how machines behave. Today, we'll build on that knowledge by learning how engineers measure what machines actually accomplish. We'll focus on three key ideas: work, energy, and power. These concepts are used everywhere in engineering, from engines to motors to turbines and industrial machines. In everyday conversation, the word work can mean almost any effort, but in engineering and physics, work has a very specific meaning. Work occurs only when a force causes an object to move through a distance. For example, pushing a box across a floor involves work because a force is applied and the box moves. Lifting a weight overhead also involves work because the object changes position. However, if you push against a wall and it doesn't move, no work is done. Even though you're using effort, there is no movement. That's why engineers often remember a simple rule: no movement means no work. The standard unit to measure the work is the joule, or J. Engineers calculate work using a simple equation. In this equation, W represents work, F represents force, and D represents distance. This formula tells us what the work increases when either the force increases or the distance increases. For example, if you push an object with a force of 15 newtons and it moves 2 meters, the work performed is 100 joules. This equation is one of the most important tools engineers use when analyzing mechanical systems. Now, let's talk about energy. Energy is the ability to do work. Every machine requires energy in some form in order to operate. One of the most important rules in engineering is that machines do not create energy. Instead, they convert energy from one form into another. For example, an electric motor converts electrical energy into mechanical energy. A battery converts chemical energy into electrical energy. Understanding how energy flows through a machine is a major part of mechanical engineering. There are many forms of energy, but two of the most important mechanical forms are potential energy and kinetic energy. Potential energy is stored energy that is ready to be released. A raised object has a gravitational potential energy, and a compressed string stores elastic potential energy. Kinetic energy, on the other hand, is the form of motion, is the energy of motion. A moving car has kinetic energy. A spinning wheel has kinetic energy. A falling object has kinetic energy as it moves. Machines constantly convert between these two forms. A roller coaster is a great example. As it climbs a hill, it gains potential energy. As it descends, the potential energy becomes kinetic energy. This process repeats throughout the ride. Now, let's introduce power. Power measures how quickly work is done. Imagine two cranes lifting the same load to the same height. If one crane completes the task in half the time it is producing more power. Both cranes perform the same amount of work. The difference is the speed at which the work was completed. The standard unit of power is watt, abbreviated as capital W. The Watt is named after James Watt, whose improvements to the steam engine helped drive the Industrial Revolution. Engineers calculate power using another important equation. Here, P represents power, W represents work, and T represents time. This equation shows a very important relationship. If the amount of work stays the same, but the time decreases, power increases. In simple terms, doing the same job faster requires more power. For example, a 100-watt light bulb uses 100 joules of energy every second that it operates. This concept allows engineers to compare the performance of different machines and energy systems. So let's bring everything together with a real engineering example. A car engine contains chemical energy stored in fuel. When the fuel burns, chemical energy is converted into thermal energy. That thermal energy creates force inside the engine that moves the pistons. The pistons perform mechanical work and produce rotational motion through the crankshaft. Finally, power is delivered to the wheels to move the vehicle. This example demonstrates how work, energy, and power are connected. Energy provides the ability to do work. Work creates motion, and power describes how quickly that work is performed. Let's review what we learned today. We defined work as a force acting through distance and learned how engineers calculate it. We explored energy as the ability to do work and discussed how machines convert energy from one form to another. We compared potential and kinetic energy and saw how machines continuously transform between them. We also learned that power measures how quickly work is done and introduced the power equation. Finally, we examined the car engine as a real-world example that combines all three concepts. In the next lesson, we'll explore gears and mechanical advantage. We'll answer an interesting question: how can machines change speed and force without changing the total work done? Thank you for watching, and I'll see you in lesson 6.